Did extremophile microorganisms come from space? And if so, did they contribute to the emergence of life on Earth? When we ask how life began on Earth, we usually imagine a fairly orderly scenario. A young planet, liquid water, a primitive atmosphere, energy from the sun or lightning, and slowly, out of simple chemistry, life emerged. It's a nice story. The problem is that the evidence accumulated over recent decades doesn't really fit such simplicity. As science progresses, we are discovering two challenging facts. Life is far more resilient than we once thought, and the building blocks of life are far more widespread in the universe than we ever imagined. And when these two facts meet, a question arises that is impossible to ignore. Could it be that life on Earth did not begin here entirely on its own? Not necessarily aliens, not intelligent beings, but something far more basic, microscopic, resilient, and almost indestructible. Life that shouldn't exist, but does. Extremophiles, the rule breakers of biology. The term extremophiles refers to organisms that live in conditions once considered completely incompatible with life. And this is not a fringe curiosity, it is an entire world. Extreme heat. There are bacteria and archaea that live in hydrothermal vents deep in the ocean, at temperatures exceeding 100 degrees Celsius. No sunlight, no photosynthesis. Their energy comes from chemical reactions. Extreme cold. Bacteria have been found frozen in glaciers and permafrost for tens of thousands of years, and when thawed, they returned to activity. Extreme pressure. At depths of kilometers below sea level, under pressures that would crush any multicellular organism, entire ecosystems exist. Acidity and salinity. Some organisms thrive in extremely acidic environments, pH levels approaching battery acid. Others live in hypersaline pools, several times saltier than seawater. But none of this is the real surprise. Tardigrades, organisms that challenge the definition of life. Tardigrades, or water bears, are tiny multicellular organisms that look almost cute. Biologically, however, they are anomalies on a cosmic scale. They can dehydrate almost completely, halt nearly all metabolic activity, survive extreme radiation, survive complete vacuum. In a state known as cryptobiosis, the tardigrade nearly switches itself off. There is no significant metabolism, no normal biological activity, and when conditions become favorable again, it simply comes back to life. In experiments, tardigrades were exposed directly to open space, without protection, and survived. And here something unsettling emerges. If a multicellular organism can survive space, what about organisms that are far simpler? So what actually comes from space? Organic chemistry, not a question, a fact. Today there is no serious debate about this. Carbonaceous meteorites contain complex organic compounds, including amino acids, nitrogenous bases, long-chain carbon molecules. Some amino acids were found with chiral ratios that do not match terrestrial biology, a strong indication that they are not contamination from Earth. The implication is profound. The universe knows how to produce the building blocks of life, without life. Microscopic structures, controversial but intriguing. In several meteorites, the most famous originating from Mars, microscopic structures were found that resemble cells, bacteria, biological colonies. The problem: similar structures can also form through non-biological geological processes, so science remains cautious. No declarations, no proof, but also no absolute dismissal. And this is exactly where interesting questions begin. Exposure to space experiments. Experiments conducted on the International Space Station exposed bacteria, spores, lichens to cosmic radiation, vacuum, and extreme temperature fluctuations. Some survived for months, even years. This does not prove that life arrived from space, but it does show that such a journey is at least theoretically possible. And this is where the theory of panspermia enters the discussion. What does panspermia actually propose? Panspermia does not claim that intelligent life came here. It proposes something far more modest and far more challenging. Weak panspermia. The building blocks of life came from space: amino acids, organic molecules, chemical catalysts. Earth did not start from zero. Intermediate panspermia. Complex pre-biological chemical systems arrived from space. Not full life, but something already capable of partial replication. Strong panspermia. Resilient microorganisms arrived via asteroids or comets. This is the most controversial version, and also the least accepted by the scientific establishment. If there is plausibility that life, or at least its components, came from space, could they have contributed to the emergence of life as we know it? To answer whether microorganisms, possibly even non-terrestrial in origin, could have influenced the development of life, we must first ask a more fundamental question. Do we know of organisms on Earth that fundamentally altered the course of evolution? The answer is unequivocal. Yes. Not one, not two, but several of the greatest transformations in the history of life were driven by microscopic organisms. The strongest example? Cyanobacteria and the Great Oxygenation Event. Around 2.4 billion years ago, Earth was a completely different place. Almost no free oxygen, a reducing atmosphere, very simple anaerobic life. Then cyanobacteria appeared, single-celled organisms that did something seemingly small: photosynthesis. But not just any photosynthesis. Photosynthesis that produces oxygen as a byproduct. At first, oxygen was toxic to most existing life. Massive extinctions of anaerobic organisms occurred. But in the long term, the ozone layer formed. Far more efficient metabolism became possible. The door opened for complex multicellular life. Critical point: cyanobacteria did not intend to create complex life. They simply altered the planet's chemistry. And that changed everything. What about the secretion of helpful substances? Some microorganisms secrete organic polymers, protective layers, biofilms, compounds that stabilize aqueous environments. Biofilms, for example, shield against radiation, retain moisture, create stable microenvironments. Such environments may have protected fragile molecules, enabled more complex chemical reactions, accelerated the transition from pre-life to life. Would a non-terrestrial organism have needed to do anything special? No. If a microscopic organism, terrestrial or extraterrestrial, were highly resilient, extremely simple, possessing a unique chemical metabolism, it would be enough for it to slightly alter its environment, introduce a new energy source, stabilize existing processes to profoundly influence the direction of evolution. We have already seen this happen. Therefore, the claim that extraterrestrial life could not have influenced Earth does not withstand historical scrutiny, because microscopic life has already transformed this planet completely, again and again, without planning, without intelligence, purely through chemistry and biology. We do not need to prove that life arrived from space to say that if it had, it would have had an impact. Earth itself demonstrates that tiny organisms can produce planetary-scale change. Conclusion. As of today, there is no direct evidence that life arrived on Earth from space. No unambiguous microorganisms have been identified in asteroids, meteorites, or samples returned from space missions. But it is equally important to say, There is also no evidence that allows us to rule out this possibility entirely. Science has firmly established several facts. The building blocks of life, complex organic compounds, are widespread in the solar system and beyond. Some microorganisms can survive conditions remarkably similar to space. Microscopic biological processes can alter planetary environments on a global scale. Collisions between asteroids, comets, and planets are common throughout the history of the solar system. In other words, the chemistry exists, the resilience exists, and the dynamical mechanism exists. What is missing is not plausibility, but direct evidence. And therefore, the true scientific question is no longer, did extraterrestrial life visit Earth, but a deeper one. Is the emergence of life a rare and unique event, or a natural outcome of chemistry under suitable conditions? If life is rare, Earth is an exception. If life is natural, Earth is simply a case where conditions persisted long enough. In this sense, Earth may not be the point of origin of life, but rather a successful continuation, where chemical and biological processes found stability, complexity, and persistence.